There is a place where the sun stops. Not in any way you could see with your eyes. The light still reaches, thin and pale, far beyond where Voyager crossed. But there is a boundary nonetheless, marked not by a wall or a gate, but by the sudden absence of something invisible. The wind that has been blowing outward from our star for 4.5 billion years. Voyager 1 crossed it in 2012, and Voyager 2 followed in 2018, slipping through a frontier that has no substance and no fixed position, a border defined only by the contest between what the sun pushes out and what the galaxy presses back. What the spacecraft found on the other side was not emptiness, but a different kind of space, older, colder, and filled with things that have never known the sun's influence. Voyager 1 is more than 15 billion miles from Earth. The number itself is difficult to hold in the mind, 15 billion, because it exceeds the scale of anything we encounter in daily experience. If you tried to count to 15 billion at one number per second, it would take you nearly 500 years. If you could drive at highway speed without stopping, the journey would consume more than 27,000 years. Light itself, crossing the void at a speed nothing else can match, takes more than 22 hours to travel from Voyager back to us. When the spacecraft sends a signal home, the message arrives carrying information about a place and time that no longer exists by the moment we receive it. The spacecraft has moved on, the solar wind has shifted, the particles Voyager measured a day ago have drifted away or been replaced by others. What we know about that distant edge is always, inevitably, a memory. At such distances, the familiar anchors of the solar system fall away. Voyager is 3 times farther from the Sun than Neptune, the outermost planet, whose orbit traces a circle more than 2.5 billion miles in radius. It is 6 times farther than Pluto at its most distant reach. The asteroid belt, the place where rocky debris from the solar system's formation still circles between Mars and Jupiter, lies so far behind Voyager now that it would take years for light from the Sun to travel from there to where the spacecraft drifts. Even the Kuiper belt, that broad disk of icy bodies extending beyond Neptune's orbit, is no longer nearby. Voyager passed through it long ago when the mission was still young and the spacecraft still received enough sunlight to use its cameras. The images it sent back during those years showed a sun that looked smaller with each passing month, a bright point slowly dimming against the black. Eventually, the cameras were turned off to conserve power, and the sun became something measured only by instruments, a source of particles and magnetic influence rather than a visible disk. The sun's light, even at Voyager's distance, has not disappeared. If you could stand on the spacecraft and look back toward the inner solar system, you would still see the sun shining, though it would appear no larger than a bright star, brighter than any other star in the sky, but no longer the overwhelming presence that defines day and night on Earth. The warmth that light once carried, the energy that evaporates oceans and drives winds and makes life possible, has spread so thin across the expanding sphere of space that it barely registers. Voyager's surface, exposed to that faint glow, hovers just a few degrees above absolute zero. The cold is not the cold of winter, or even the cold of deep space near Earth. It is the cold of a place where the sun's heat has become a whisper, a residual trace of the furnace burning at the center of the solar system. But light is only one aspect of the sun's reach. The sun does not simply shine, it exhales. From its surface, a continuous stream of charged particles flows outward in all directions, a wind composed mostly of electrons and protons torn from hydrogen atoms in the sun's outer atmosphere. This solar wind rushes away from the star at speeds ranging from 200 to 500 miles per second, far faster than any wind on Earth, fast enough to cross the distance from the sun to Earth in just a few days. It carries with it the sun's magnetic field, threads of invisible force woven through the plasma, connecting every particle to the star that released it. The wind does not blow steadily. It gusts and surges, responding to eruptions on the sun's surface, to the roiling convection of its interior, to the 11-year cycle of magnetic activity that flips the sun's poles and sends waves of energetic particles cascading through the solar system. Planets feel this wind as it flows past them, their own magnetic fields deflecting it, channeling it around their atmospheres, creating glowing auroras where it interacts with gases high above their surfaces. For billions of years, This wind has been blowing outward, filling the space around the sun with matter and energy that originated in the star's core. It defines a region, a bubble of influence that extends far beyond the orbits of the planets, far beyond the scattered ice of the Kuiper Belt, out into the space between stars. This region is the heliosphere, the sphere of the sun, and it is vast. Voyager, even after more than 4 decades of travel, spent most of its journey within it. The spacecraft crossed the orbits of Jupiter, Saturn, Uranus, and Neptune, while still bathed in the solar wind, still inside the domain where the sun's particles outnumber those from interstellar space. The heliopause, the boundary where the solar wind finally stops, lies farther out than any planet, farther than any comet observed in recorded history, farther than the vast majority of objects that orbit the sun. Voyager had to travel for 35 years, covering more than 11 billion miles before it reached that edge. The approach was gradual. There was no moment when the spacecraft passed a sign or crossed a visible line. Instead, the instruments began to detect changes in the environment, shifts so subtle that scientists debated for years whether they indicated the true boundary or merely a region of turbulence within the heliosphere itself. The density of particles fluctuated. The magnetic field twisted and realigned. Cosmic rays, high-energy particles from distant stars and exploded suns, grew more intense as the solar wind's shielding effect diminished. Voyager was entering a frontier defined not by geography, but by physics, a place where 2 opposing forces meet, and the stronger one, for the first time in billions of miles, is not the sun. The sun's dominion over space is not a matter of territory in any political sense, not a claim enforced by borders or treaties, but rather a consequence of physics, the inevitable result of matter and energy flowing outward from a star. Every second, the sun loses approximately 4 million tons of mass, converted into energy that radiates in all directions and into particles that stream away as the solar wind. This is not a catastrophic hemorrhaging, but a steady, sustainable process that the sun has maintained for billions of years and will continue for billions more. The mass lost represents only a tiny fraction of the sun's total bulk, so small that the star's gravitational pull on the planets has changed imperceptibly over the entire span of human civilization. Yet that flow of particles, sustained across eons, creates a bubble of influence that extends farther than anything else the sun produces. The solar wind does not travel forever at the same speed it leaves the sun. Near Earth, the wind moves at an average velocity of about 250 miles per second, fast enough to circle the equator in less than 2 minutes. At that speed, the particles carry significant kinetic energy, and their density, though extremely low by earthly standards, is sufficient to exert pressure on anything they encounter. Spacecraft in Earth orbit must account for this pressure when calculating trajectories. Comets passing through the inner solar system develop tails that stream away from the sun not because of light alone, but because the solar wind physically pushes the gas and dust liberated from the comet's icy nucleus. The wind is thin, almost ghostly by the standards of an atmosphere, but it is real and it is powerful. As the solar wind moves farther from the sun, it spreads across an ever-expanding sphere of space. The same number of particles that flowed through a given area near Earth must, by the time they reach twice that distance, spread across 4 times the area. At 3 times the distance, the area is 9 times larger. This is the geometry of expansion, the inevitable dilution that affects anything radiating outward from a central source. The density of the solar wind decreases with the square of the distance, meaning that at Voyager's location, more than 15 billion miles from the sun, the wind is hundreds of times thinner than it is near Earth. The particles are farther apart, the collisions between them less frequent, the collective pressure they exert diminished. But the solar wind does not simply thin, it also slows. The sun's gravity, though weakening with distance, never entirely vanishes. Every particle in the solar wind is still bound, however loosely, to the star that released it, and that gravitational tether exerts a drag, pulling back against the outward motion. The effect is subtle at first, barely noticeable in the inner solar system, where the wind's initial speed is so high that gravity's influence seems negligible. But over billions of miles, the cumulative effect becomes significant. By the time the solar wind reaches the outer edges of the heliosphere, it has slowed to a fraction of its original velocity. Some of the wind's kinetic energy has been converted back into potential energy, the energy of position within the sun's gravitational field, and the particles drift rather than race. At the same time, the solar wind encounters resistance from the space it enters. Interstellar space is not empty. Between the stars, the galaxy is filled with a thin medium of gas and dust, the remnants of ancient supernovae, the debris of stellar winds from other stars, the raw material from which new stars and planets will eventually form. This interstellar medium is even less dense than the solar wind, containing on average only a few atoms per cubic inch, compared to the solar wind's hundreds of particles per cubic inch near Earth. But interstellar space is vast, and the collective pressure of all that diffuse matter, accumulated across light years, is enough to resist the sun's outward push. The solar wind, expanding outward, meets the interstellar medium pressing inward, and somewhere in that meeting the two forces balance. The boundary where this balance occurs is not fixed in space. It shifts and undulates, responding to changes in the solar wind's strength and in the density of the interstellar medium through which the heliosphere moves. When the sun is more active, ejecting more particles and more energetic storms, the solar wind pushes farther outward and the heliopause expands. When the sun is quieter, the boundary contracts. The heliosphere also moves through the galaxy as the sun orbits the galactic center, carrying its bubble of influence with it like a ship moving through water, and the interstellar medium it encounters varies in density and composition. In some directions, the medium is denser and the heliopause lies closer to the sun. In others, the medium is thinner and the boundary extends farther. The shape of the heliosphere is not a perfect sphere, but something more complex, perhaps elongated, perhaps asymmetric, with a tail stretching behind the sun's motion through the galaxy like the wake of a boat. Voyager, traveling outward, was moving toward a boundary that scientists knew existed, but had never directly measured. Theoretical models, constructed from observations of the solar wind near Earth and from comparisons with other stars surrounded by their own stellar winds, suggested that the heliopause lay somewhere between 10 and 15 billion miles from the sun, but the uncertainty was large. The spacecraft carried instruments designed to detect the transition, sensors that could measure changes in particle density, in magnetic field orientation, in the energy spectrum of cosmic rays arriving from interstellar space. These instruments had been operating for decades, recording data as Voyager moved farther from home, watching for the first signs that the sun's wind was beginning to falter. The data showed a gradual change, not a sudden shift. The solar wind's speed, already slow compared to its velocity near Earth, decreased further. The magnetic field carried by the wind began to fluctuate more wildly, tangled and compressed by the pressure from interstellar space. Cosmic rays, high-energy particles that the solar wind normally deflects or slows, increased in intensity as the wind's shielding effect weakened. Voyager was entering a region where the sun's influence, though still present, was no longer dominant, a place where the rules that governed the inner solar system no longer fully applied. The heliosphere is, among other things, a shield. This is not its purpose. The solar wind does not blow outward with the intention of protecting anything, but it is one of its consequences. The charged particles streaming from the sun, spreading outward in all directions, create a region where the interstellar medium is held at bay, where the density and composition of space are determined by the sun rather than by the galaxy. Within this bubble, the solar system exists in a kind of isolation, surrounded by but separated from the rest of the Milky Way. The separation is not absolute. Matter and energy still cross the boundary in both directions, but it is significant enough that the environment inside the heliosphere differs fundamentally from the environment beyond it. Cosmic rays are one of the things the heliosphere deflects. These are particles, mostly protons but also heavier atomic nuclei and even a small fraction of electrons that travel through interstellar space at velocities approaching the speed of light. They originate from sources scattered throughout the galaxy, supernova explosions that shred dying stars and accelerate their debris to relativistic speeds, pulsars whose rotating magnetic fields whip particles into energetic spirals, shockwaves from colliding stellar winds, and possibly the supermassive black hole at the galaxy's center, whose gravitational and magnetic forces are so intense that they can accelerate particles to energies far beyond anything achievable in human-built accelerators. Some cosmic rays come from even farther away from other galaxies, their origins so distant that tracing them back to a specific source becomes impossible. These particles have been traveling for millions of years, crossing the vast emptiness between stars, and when they encounter the heliosphere, they find an obstacle. The solar wind, though thin, is not passive. Its magnetic field, carried outward from the sun, creates a tangled, turbulent barrier that cosmic rays must navigate. As the high-energy particles try to enter the heliosphere, they are deflected by the magnetic fields, their trajectories bent and twisted. Some are turned back entirely, unable to penetrate the outer layers of the solar wind. Others lose energy as they push inward, slowed by countless interactions with the magnetic field lines and with the charged particles of the solar wind itself. Only the most energetic cosmic rays, those with velocities so close to the speed of light that their momentum overwhelms the resistance, manage to reach the inner solar system in significant numbers. The heliosphere does not create a perfect barrier. Cosmic rays still arrive at Earth, still collide with the atmosphere, and create showers of secondary particles that reach the surface, but the shielding effect is substantial. Outside the heliosphere, in interstellar space, the intensity of cosmic rays is perhaps twice as high as it is near Earth, perhaps more depending on the direction and the local density of the interstellar medium. This shielding matters, though its importance is difficult to quantify with precision. Cosmic rays, when they strike living tissue, can damage DNA, increasing the risk of cancer and other radiation-related illnesses. On Earth, the atmosphere provides additional protection, absorbing most of the cosmic rays before they reach the surface, but spacecraft and astronauts traveling beyond Earth's orbit are more exposed. The particles also interact with spacecraft electronics, occasionally causing malfunctions or errors in computer systems, and over time they degrade materials, weakening structures and reducing the efficiency of solar panels. A mission to Mars or to the outer planets must account for the increased cosmic ray exposure that comes with leaving Earth's protective magnetic field. A mission beyond the heliopause into interstellar space would encounter even higher levels of radiation, a chronic, unavoidable presence that any future crewed expedition would need to shield against or accept. But the heliosphere's influence extends beyond radiation shielding. The space within it is, in a sense, chemically distinct from the space outside. The solar wind carries with it atoms from the sun's atmosphere, primarily hydrogen and helium, the lightest and most abundant elements in the universe, but also trace amounts of heavier elements forged in the sun's core, or inherited from the molecular cloud that collapsed to form the solar system billions of years ago. These particles mix and interact, creating a plasma, a state of matter where electrons are stripped from atoms, leaving positively charged ions and free electrons flowing together, that fills the heliosphere with a subtle but measurable signature of the sun's composition. The interstellar medium, by contrast, contains atoms from many sources: hydrogen and helium left over from the Big Bang, oxygen and carbon and nitrogen produced in the cores of earlier generations of stars, iron and silicon and nickel forged in supernovae. The proportions differ, the isotopes differ, the temperature and density differ. Crossing the heliopause means entering a region of space that has never been inside a stellar wind, a place where the matter is older and more heterogeneous, shaped by the history of the entire galaxy rather than the history of a single star. The heliosphere also creates a kind of stillness, or at least a relative calm. The interstellar medium is not static. It flows and swirls, driven by the motion of the galaxy's spiral arms, by the pressure waves from distant supernovae, by the magnetic fields that thread through the space between stars. The Sun and its heliosphere move through this medium at a velocity of about 45,000 miles per hour relative to the surrounding stars, fast enough to create a bow shock, a region where the interstellar medium piles up ahead of the heliosphere, compressed and heated by the encounter. like water building up in front of a moving ship. Some models suggest that the heliosphere has a tail, a wake stretching behind the sun's motion, where the solar wind extends farther before mixing with the interstellar medium. Inside the heliosphere, the solar wind dominates, and the interstellar flow is kept at a distance. Outside, the spacecraft would be exposed to the currents and eddies of the galaxy's own weather, subject to forces that have nothing to do with the sun. Voyager was built to leave the heliosphere, though the mission's designers did not know precisely when or where the crossing would occur. The spacecraft carried no shielding beyond what was necessary to protect its instruments from the sun's radiation, no armor against the higher cosmic ray flux it would encounter in interstellar space. Its power source, a radioisotope thermoelectric generator, converting the heat from decaying plutonium into electricity, would continue to function regardless of the environment, though its output would decline gradually as the plutonium aged. The instruments would keep recording until the power ran out, expected sometime in the 2020s or early 2030s, and the data would keep flowing back to Earth as long as the spacecraft's antenna remained pointed in the right direction, and the signal remained strong enough to be detected across the growing distance. The heliosphere is not uniform. It does not end abruptly at a single distance from the sun, nor does it maintain the same properties throughout its volume. Instead, it contains regions, layers defined not by walls or surfaces, but by gradual transitions in the behavior of the solar wind and the forces acting upon it. These regions blend into one another over distances that can span hundreds of millions of miles, making it difficult to say precisely where one ends and another begins. Voyager, moving outward, crossed through these regions one by one, measuring the changes as the sun's influence weakened and the presence of interstellar space grew stronger. The first major boundary Voyager encountered, long before reaching the heliopause itself, was the termination shock. This is the place where the solar wind, which has been flowing outward at supersonic speed since leaving the sun, suddenly slows to subsonic velocities. The term shock in physics refers to a discontinuity, a place where conditions change sharply across a narrow region rather than smoothly over a long distance. In the case of the termination shock, the solar wind encounters increasing pressure from the interstellar medium pressing inward, and at a certain distance from the sun, roughly 8 to 9 billion miles, though the exact location varies with solar activity, the wind can no longer maintain its speed. It slows abruptly, compressing and heating as its kinetic energy converts into thermal energy and turbulence. Voyager 1 crossed the termination shock in December 2004 at a distance of about 8.7 billion miles from the sun. The spacecraft's instruments detected the transition over the course of several days, recording sudden increases in the density and temperature of the solar wind particles and changes in the magnetic field's orientation. The shock was not a single instant, but a process, a region of chaotic turbulence where the smooth, fast flow of the solar wind broke down into eddies and waves. Voyager 2, following a different trajectory through a different part of the heliosphere, crossed the termination shock in August 2007, about 1 billion miles closer to the sun than its twin. The difference in crossing distances confirmed what scientists had suspected. The heliosphere is not perfectly symmetrical. Its shape responds to variations in the solar wind's strength and to the uneven pressure of the interstellar medium surrounding it. Beyond the termination shock lies a region called the heliosheath, the outer layer of the heliosphere where the solar wind has slowed but still flows outward, compressed and turbulent, pushing toward the heliopause. The heliosheath is thick, spanning several billion miles between the termination shock and the heliopause itself, and the conditions within it are complex. The solar wind, no longer moving in a simple radial pattern away from the sun, becomes tangled by the magnetic forces and pressure gradients acting on it. Some of the wind's particles are deflected, turned sideways, flowing along the boundary rather than outward through it. Others are reflected back toward the sun, creating a population of particles moving inward against the general outward flow. The magnetic field lines, which near Earth run smoothly outward from the sun in a spiral pattern shaped by the sun's rotation, become compressed and twisted in the heliosheath, piling up against the resistance of the interstellar medium. Voyager spent years crossing the heliosheath, longer than it had spent traveling from Earth to the termination shock. The instruments recorded fluctuations in the particle density, the magnetic field strength, and the intensity of cosmic rays, all varying in ways that suggested the spacecraft was moving through a dynamic, unstable region. There were periods when the data seemed to indicate that Voyager had crossed the heliopause, only for the measurements to shift again, suggesting the spacecraft had encountered a temporary disturbance or a localized structure within the helios sheath rather than the true boundary. Scientists debated the meaning of these fluctuations. Some argued that the heliopause itself was not a sharp boundary, but a broad transition zone, a region where the solar wind and the interstellar medium mixed and interacted over a thickness comparable to the helios sheath itself. Others maintained that the heliopause was a distinct boundary, but that its position moved in response to changes in the solar wind, so that Voyager might cross it multiple times as the boundary shifted back and forth across the spacecraft's location. The question of where exactly the heliosphere ends is not merely semantic. It reflects a deeper uncertainty about how to define a boundary when the transition is gradual and when different physical quantities, particle density, magnetic field orientation, cosmic ray intensity, change at different rates and at different distances. The heliopause, in principle, is the place where the outward pressure of the solar wind equals the inward pressure of the interstellar medium, but measuring that balance directly is not straightforward. The solar wind's pressure depends on its density, temperature, and velocity, all of which vary with time and position. The interstellar medium's pressure depends on its own density and on the magnetic field it carries, both of which Voyager could only measure after crossing the boundary. The spacecraft's instruments could detect the consequences of the transition, the drop in solar wind particles, the increase in interstellar particles, the reorientation of the magnetic field, but translating those measurements into a precise definition of the boundary required interpretation and judgment. In 2012, Voyager 1's data began to show a significant and sustained change. The intensity of solar wind particles, which had fluctuated but remained detectable throughout the helios sheath, dropped to nearly zero. At the same time, the count of cosmic rays increased, reaching levels consistent with what would be expected in interstellar space. The magnetic field, which had been highly variable in the helios sheath, settled into a more stable orientation, pointing in a direction that seemed to align with the interstellar field rather than the Sun's field. These changes occurred over the course of a few weeks in August 2012, and after months of analysis and debate, the Voyager team concluded that the spacecraft had crossed the heliopause. Voyager 1 had left the heliosphere and entered interstellar space, becoming the first human-made object to do so. Voyager 2 followed in November 2018, crossing the heliopause at a distance of about 11 billion miles from the Sun, roughly a billion miles closer than Voyager 1 had crossed 6 years earlier. The difference in crossing distances and the differences in the magnetic field measurements the two spacecraft recorded provided the first direct evidence of the heliosphere's asymmetry and the first glimpses of how the boundary's properties vary with location. The two spacecraft, traveling in different directions, had sampled two different parts of the heliopause, and the data they returned would allow scientists to begin mapping the shape and structure of the boundary in ways that had never been possible before. The crossing itself was invisible. There was no marker, no change in color or temperature that a human observer could have perceived, no physical barrier that the spacecraft pushed through. If you had been able to stand on Voyager as it passed from the heliosphere into interstellar space, you would have seen nothing different from what you had seen for years before. The same distant stars, the same faint glow of the sun behind you, the same absolute blackness in every direction. The boundary exists only in the behavior of particles and fields, in quantities that require instruments to detect and months of analysis to interpret. It is a frontier defined by statistics, by the changing ratio of particles that originated in the Sun to particles that came from elsewhere, by the gradual reorientation of magnetic field lines whose influence is felt only by charged particles too small to see. This is the nature of most boundaries in space. Unlike borders on Earth, which can be marked with walls or signs or rivers, the divisions between different regions of the cosmos are almost always invisible, defined by forces rather than by geography. The boundary between Earth's atmosphere and space is a convention, a line drawn at an arbitrary altitude where the air becomes too thin to support conventional flight, but where molecules of nitrogen and oxygen still exist in measurable quantities. The edge of a planet's magnetosphere, the region where its magnetic field dominates over the solar wind, shifts continuously with the wind's pressure, expanding and contracting over the course of hours or days. Even the surfaces of stars, which seem so definite when viewed from a distance, are merely places where the density of gas drops below a certain threshold, the photosphere giving way gradually to the chromosphere and then to the corona, each layer blending into the next without a clear dividing line. The heliopause is no different in this respect, yet it carries a significance that other boundaries do not. It marks the limit of the sun's direct influence, the edge of the region where solar processes dominate the environment. Inside the heliosphere, the matter that fills space, however thin it may be, came from the sun. The magnetic field, though tangled and twisted by the solar wind's turbulence, originated in the sun's interior and retains a connection, however distant, to the star's dynamo. The energy that flows through the plasma was released in the sun's core, carried outward by radiation and convection, and finally expelled into space as kinetic energy and heat. Outside the heliopause, none of this is true anymore. The matter Voyager encounters in interstellar space has never been part of the sun, never felt its gravity except as one distant mass among billions in the galaxy. The magnetic field is the galaxy's field, shaped by the collective motion of stars and the rotation of the Milky Way itself, stretched and amplified by the same dynamo processes that operate in the sun, but occurring on scales thousands of times larger. The particles and radiation that fill interstellar space come from sources scattered across light years, some from stars that have been dead for millions of years, their light still traveling toward Earth, while their remains drift as nebulae or compact remnants. To cross the heliopause is, in a sense, to leave the solar system's immediate neighborhood and enter the larger community of the galaxy. The solar system, as a gravitational entity, extends far beyond the heliopause. Comets in the Oort cloud, the vast spherical shell of icy bodies surrounding the sun, orbit at distances that may reach halfway to the nearest star, and they remain bound to the sun by gravity, even though they lie deep within interstellar space. But the heliosphere, the region of the sun's active influence, is smaller and more tightly defined. Voyager, by crossing the heliopause, passed from a region shaped by a single star into a region shaped by the galaxy as a whole, from a place where the sun's present-day activity matters to a place where only its gravity and light, both weakened by distance, still have any effect. The spacecraft itself did not change. Its instruments continued to operate as they had for decades, measuring the same quantities they had always measured. Its trajectory continued along the same path it had been following since its encounter with Saturn in 1980, coasting under its own momentum with no fuel left to alter course. The only difference was in what those instruments detected: fewer solar wind particles, more cosmic rays, a magnetic field that no longer fluctuated wildly, but instead held a steady orientation aligned with the interstellar field. These changes unfolded over weeks, not seconds, and even after the transition was complete, it took time for scientists to be confident that what they were seeing was not another temporary disturbance, but the actual crossing into interstellar space. Part of the difficulty lay in the nature of the data itself. Voyager's signal, arriving at Earth more than 22 hours after being transmitted, carried information about the environment where the spacecraft had been nearly a day earlier. By the time scientists received the data, analyzed it and discussed its implications, Voyager had moved millions of miles farther along its trajectory. If the heliopause was shifting, as it seemed to do in response to fluctuations in the solar wind, then the spacecraft might cross back and forth multiple times, each crossing separated by weeks or months, and the delayed communication would make it impossible to track these movements in real time. The scientists had to rely on patterns in the data, looking for sustained changes rather than brief fluctuations, comparing measurements across different instruments to see if they told a consistent story. The story that emerged from Voyager 1's data in 2012, and later from Voyager 2's data in 2018, was one of a boundary that, while not instantaneous, was nevertheless distinct. The solar wind particles did not gradually decrease over billions of miles. They dropped sharply, from detectable levels to nearly zero over a span of just a few weeks. The cosmic ray intensity did not increase smoothly. It jumped upward in a matter of days, reaching a new, higher level that remained stable afterward. The magnetic field, which had been chaotic in the heliosheath, settled into a configuration that matched theoretical predictions for the interstellar field's orientation. These changes, taken together, indicated that Voyager had crossed a real boundary, a place where the balance of forces shifted decisively from solar to interstellar dominance. Yet the crossing left questions unanswered, details that the spacecraft's instruments could not resolve. The thickness of the boundary, whether it was a sharp transition just a few million miles wide or a broader zone spanning hundreds of millions of miles, remained uncertain. The structure of the magnetic field at the boundary, and how it connected the Sun's field to the interstellar field, was more complicated than the models had anticipated. The exact density and composition of the interstellar medium immediately outside the heliopause could only be inferred from indirect measurements, and those inferences carried significant uncertainties. Voyager's instruments are remarkably simple compared to the spacecraft that have been launched in more recent decades. They were designed in the 1970s, built with the technology available at that time, when a computer's memory was measured in kilobytes rather than gigabytes, and when the most sophisticated processors could perform only a few 100,000 operations per second. The spacecraft carries no cameras. Those were turned off in 1990 to conserve power, after taking a final sequence of images that included the famous pale blue dot photograph of Earth seen from beyond Neptune's orbit. What remains active are instruments designed to measure particles and fields, quantities that cannot be seen with the eye, but that define the properties of the space through which Voyager travels. The plasma science instrument detects charged particles in the solar wind, measuring their density, velocity, and temperature by analyzing how they interact with electric fields generated by the instrument itself. When a charged particle enters the detector, it is deflected by the electric field, and the amount of deflection depends on the particle's energy and charge. By measuring the distribution of deflections, the instrument can determine not just how many particles are present, but also how fast they are moving and in what direction. This was the instrument that detected the drop in solar wind density when Voyager 1 crossed the heliopause, the sudden absence of the particles that had been present in varying numbers throughout the entire journey from Earth. The solar wind did not fade gradually. It disappeared, dropping from detectable levels to effectively zero over a period of just a few weeks, indicating that the spacecraft had moved from a region dominated by solar particles to a region where those particles no longer penetrated in significant numbers. The cosmic ray detector measures high-energy particles arriving from outside the solar system, counting how many particles strike the detector per second and analyzing their energies. Cosmic rays are more penetrating than the solar wind particles, capable of passing through metal and plastic and even human tissue, and the detector uses stacks of silicon wafers to track their paths and determine their energies. When Voyager crossed the heliopause, the cosmic ray count increased sharply, jumping from the levels measured in the heliosheath to levels consistent with what would be expected in interstellar space, where the solar wind's shielding effect no longer reduces the incoming flux. The increase was not uniform across all energies. Lower energy cosmic rays, which are more easily deflected by magnetic fields, showed a larger increase than higher energy cosmic rays, which had been able to penetrate deep into the heliosphere even before Voyager reached the boundary. The pattern of the increase, the way different energies responded differently to the crossing, provided information about the strength and structure of the magnetic fields on both sides of the heliopause. The magnetometer measures the magnetic field's strength and direction, detecting the invisible lines of force that thread through space and influence the motion of charged particles. Magnetic fields in space are weak by terrestrial standards. The interstellar field that Voyager measures is roughly 10,000 times weaker than the magnetic field at Earth's surface. But they are pervasive, filling the space between stars and shaping the behavior of plasmas and cosmic rays across vast distances. The magnetometer consists of two sensors mounted on a boom extending from the spacecraft's body, placed far enough from the spacecraft's electronics that the magnetic fields generated by those systems do not overwhelm the signal from the external field. The sensors measure the field continuously, recording its strength and direction multiple times per second, and the data they return reveals how the field changes as Voyager moves through different regions of space. In the Helios heath, the magnetic field was turbulent, its direction shifting erratically as the compressed solar wind churned and mixed. The field's strength varied from moment to moment, sometimes doubling or halving over the course of hours, reflecting the dynamic, chaotic conditions in that region. But when Voyager crossed the heliopause, the field became more stable. Its direction settled into a consistent orientation, pointing roughly perpendicular to the plane of the solar system, aligned with what theoretical models predicted for the interstellar field threading through the local region of the galaxy. The field's strength remained weak, but its steadiness contrasted sharply with the variability Voyager had experienced in the Helios sheath, suggesting that the spacecraft had entered a region where the sun's influence no longer dominated, and where the larger-scale structure of the galaxy's magnetic field could be detected directly. These three types of measurements, plasma particles, cosmic rays, and magnetic fields, provided the evidence for Voyager's crossing. No single measurement was sufficient on its own. The plasma instrument could detect the disappearance of solar wind particles, but it could not confirm that the spacecraft had entered true interstellar space rather than just a transient bubble or void within the Helios sheath. The cosmic ray detector could measure the increase in high-energy particles, but cosmic ray intensity also fluctuates in response to solar activity, and an increase alone did not prove that Voyager had crossed the boundary. The magnetometer could track the field's reorientation, but magnetic field lines can twist and reconnect in complex ways, and a change in direction might reflect local turbulence rather than a transition to a fundamentally different region. It was only by combining all three types of data, looking for correlated changes that occurred at the same time and persisted for months afterward, that scientists could conclude with confidence that the boundary had been crossed. The conclusion was not immediate. When Voyager 1's data first began to show the changes in August 2012, the team was cautious. They had seen fluctuations before, temporary shifts that resembled a crossing, but turned out to be structures within the Helios sheath. It took additional months of data and additional analysis comparing the patterns to theoretical predictions before the team announced in September 2013 that Voyager 1 had indeed entered interstellar space. Even then, some scientists questioned the interpretation, pointing to anomalies in the magnetic field data that seemed inconsistent with the expected properties of the interstellar field. The debate continued for years, with new papers offering alternative explanations or refining the models to account for the discrepancies. By the time Voyager 2 crossed the heliopause in 2018, providing a second set of measurements from a different location, the evidence had become overwhelming, and the remaining doubts faded. The spacecraft themselves do not know what they have discovered. They are machines, executing commands uploaded from Earth, recording data according to pre-programmed sequences, transmitting that data back across billions of miles with no awareness of its significance. The instruments measure particles and fields because that is what they were built to do, not because they understand the importance of those measurements. The knowledge exists only in the minds of the scientists who receive the data, who spend years studying it, debating its meaning, constructing models to explain it, and gradually building a picture of what interstellar space is like and how it differs from the space within the heliosphere. Interstellar space is not empty, but it is emptier than almost anywhere else in the universe. The density of matter there is so low that it defies intuitive understanding, approximately 1 atom per cubic inch, perhaps fewer in some regions, perhaps a few more in others, depending on local conditions and the history of stellar activity in the surrounding area. By comparison, the air you breathe contains roughly 1 billion trillion molecules in the same volume, a number so large that even the thinnest vacuum achievable in a laboratory on Earth remains incomparably denser than the space between stars. The best vacuum chambers, evacuated to pressures that would be considered perfect by any practical standard, still contain millions of molecules per cubic inch. Interstellar space, measured by Voyager's instruments, exists at a level of emptiness that cannot be replicated on Earth, a void so profound that matter becomes almost incidental, a sparse scattering of particles drifting across distances where collisions between them are rare events separated by years or decades. The atoms that do exist in interstellar space are predominantly hydrogen, the simplest and most abundant element in the universe, the raw material from which stars form and the primary constituent of the gas clouds that fill the space between them. Most of these hydrogen atoms are neutral, meaning they retain their single electron and carry no net electric charge, unlike the ionized hydrogen that makes up much of the solar wind. Neutral atoms behave differently from ions. They are not deflected by magnetic fields, not swept along by the solar wind's flow, not accelerated by electric fields. They drift through space under the influence of gravity and their own momentum, indifferent to the electromagnetic forces that dominate the behavior of plasmas. This neutrality makes them difficult to detect directly because the instruments that measure charged particles, like Voyager's plasma science instrument, cannot sense them. Their presence must be inferred from other measurements, from the way they interact with ions and electrons, from the light they absorb or emit when struck by high-energy radiation, from the secondary particles they produce when cosmic rays collide with them. Voyager's instruments, after crossing the heliopause, detected an increase in the density of electrons, the negatively charged particles that balance the positive charge of ions in a plasma. The electron density in interstellar space, as measured by the plasma wave instrument, was higher than it had been in the heliosheath, though still extraordinarily low by any terrestrial standard, roughly 10,000 electrons per cubic inch compared to a few thousand in the outer heliosheath. This increase suggested that the interstellar medium contains a mix of neutral atoms and ionized plasma, with the ions and electrons making up a small fraction of the total mass, but contributing significantly to the region's electrical properties. The ionization likely comes from the same high-energy cosmic rays and ultraviolet light from distant stars that permeate interstellar space, stripping electrons from neutral atoms and creating a tenuous but pervasive plasma that conducts electric currents and interacts with magnetic fields. The temperature of the interstellar medium, as inferred from the motion of the particles Voyager detected, was also higher than expected, not hot in the sense of radiating heat or glowing visibly, but hot in the sense that individual particles move at high velocities, carrying significant kinetic energy, even though their collective density is so low that the total thermal energy in any given volume is negligible. The electrons measured by Voyager had temperatures of several thousand degrees Kelvin, meaning they were moving at speeds of hundreds of miles per second, far faster than the thermal motion of molecules in Earth's atmosphere. This is a characteristic of the interstellar medium in the vicinity of the Sun, where the remnants of ancient supernova explosions and the cumulative effects of stellar winds from many stars have heated the gas and stirred it into motion. The interstellar medium is not uniform. Some regions are cold and dense, others hot and thin, and the Sun happens to be located in a relatively warm, low-density region called the local interstellar cloud, or sometimes the local fluff, a name that captures both its modest size and its somewhat uncertain boundaries. The magnetic field in interstellar space, as measured by Voyager's magnetometer, aligned roughly in the direction that theoretical models had predicted, but its strength was somewhat higher than the models suggested. The field is weak, only a few microgauss, about 100,000th the strength of Earth's magnetic field at the surface, but it is not negligible. This field threads through the galaxy, shaped by the rotation of the Milky Way and by the motion of charged particles on scales spanning thousands of light years. It influences the paths of cosmic rays, bending their trajectories and making it difficult to trace them back to their sources. It also plays a role in the structure of the heliosphere itself, because the interstellar field presses against the heliopause from the outside, contributing to the boundary's shape and position. The fact that Voyager measured a field stronger than expected suggests that the local interstellar medium may be more magnetized than average, or that the models underestimated the field's strength in this particular region of the galaxy. One of the surprises in Voyager's data was the discovery that the interstellar magnetic field near the heliopause is oriented almost perpendicular to the Sun's magnetic field in the heliosheath. Inside the heliosphere, the Sun's field spirals outward, following the rotation of the Sun and the radial flow of the solar wind, creating a pattern that resembles the arms of a rotating sprinkler. The interstellar field, by contrast, runs roughly parallel to the plane of the galaxy's disk, aligned with the large-scale structure of the Milky Way's magnetic field in this region. At the heliopause, these two fields meet nearly at right angles, and the way they connect or fail to connect has implications for how particles and energy flow across the boundary. Some models predicted that the fields would merge, with field lines from the Sun reconnecting to field lines in the interstellar medium, creating pathways for particles to leak across the boundary in both directions. Other models predicted that the fields would remain separate, pressing against each other without merging, creating a sharper boundary that particles would find more difficult to cross. Voyager's measurements suggested that both processes might be occurring, with some field lines reconnecting while others remained distinct, creating a complex layered structure at the heliopause that depends on the local orientation and strength of the fields on both sides. The cosmic ray data added another layer of complexity. The intensity of cosmic rays increased when Voyager crossed the heliopause, as expected, but the increase was not uniform across all particle energies or all directions of arrival. Lower energy cosmic rays, those with energies of a few 100 million electron volts, showed the largest increase because they are the most easily deflected by the solar wind and therefore the most affected by the crossing into interstellar space. Higher energy cosmic rays, with energies of billions or tens of billions of electron volts, had already been able to penetrate deep into the heliosphere, and their intensity increased only modestly. The directional distribution of the cosmic rays also changed. Inside the heliosphere, cosmic rays arrived from all directions roughly equally because the solar wind's turbulent magnetic field scattered them and erased any directional information about their sources. Outside the heliopause, some directions showed slightly higher cosmic ray intensities than others, hinting at the possibility that Voyager might be able to detect variations in the galactic cosmic ray background related to the distribution of sources or to the structure of the interstellar magnetic field. The space Voyager entered beyond the heliopause is not the generic interstellar medium of astronomy textbooks, but a specific region with its own history and properties, a volume of gas and dust and magnetic field that has been shaped by events that occurred long before the Sun formed. This region is called the local interstellar cloud, though cloud is perhaps too solid a word for something so tenuous. It is a pocket of slightly denser, slightly warmer gas within a larger structure called the local bubble, a cavity in the interstellar medium roughly 1,000 light-years across, carved out by the combined effects of multiple supernova explosions that occurred between 10 and 20 million years ago. Those explosions, the violent deaths of massive stars that had exhausted their nuclear fuel and collapsed, released enormous amounts of energy, each one briefly outshining the entire galaxy, and the shock waves they generated swept through the surrounding space, compressing some regions and evacuating others, pushing gas and dust into shells and filaments, heating what remained to temperatures of millions of degrees. Over millions of years, the hot gas created by those supernovae has cooled and expanded, and the bubble has filled in with cooler, denser clouds that formed as the gas condensed and recombined. The local interstellar cloud is one of these condensations, a small, irregularly shaped region perhaps 30 light-years across, though its boundaries are not sharp and its exact dimensions remain uncertain. The Sun and its heliosphere lie within this cloud, or at its edge, depending on how the boundary is defined. The cloud's density, as measured by Voyager and inferred from observations of distant stars whose light passes through the cloud on its way to Earth, is low even by interstellar standards, approximately half an atom per cubic inch, though this varies from place to place within the cloud's volume. The temperature, around 7,000 degrees Kelvin as measured by the velocities of the particles, reflects the cloud's position within the local bubble, still retaining some of the heat deposited by the ancient supernovae, even as it cools toward equilibrium with the surrounding medium. The local interstellar cloud is moving relative to the Sun, or more accurately, the Sun is moving relative to the cloud, Because motion in space is always relative, and there is no fixed reference frame from which to measure absolute velocity. The Sun, carrying its planets and its heliosphere with it, travels through the galaxy at a speed of roughly 140 miles per second relative to the nearby stars, following an orbit around the galactic center that takes about 230 million years to complete. The local interstellar cloud is also moving, though at a different velocity. And the difference between the Sun's motion and the cloud's motion means that the Sun is plowing through the cloud at a relative speed of about 50,000 miles per hour. Not particularly fast by cosmic standards, but fast enough that the interstellar gas piles up ahead of the heliosphere, compressed by the encounter, and streams past the sides and behind, creating the bow shock and the tail that theoretical models predict. The Sun has been inside the local interstellar cloud for perhaps 100,000 years, a blink of time compared to the Sun's age, but long enough that the cloud's properties, its density, its temperature, its magnetic field, have shaped the heliosphere's structure and influenced the environment that Earth and the other planets experience. The matter in the local interstellar cloud is not newly created. The hydrogen and helium, the oxygen and carbon and nitrogen, the trace amounts of heavier elements like silicon and iron, all of it has been recycled through the galaxy's ecosystem for billions of years, passing through multiple generations of stars and clouds. Some of it may have been part of the molecular cloud that collapsed to form the Sun and planets 4.5 billion years ago, later ejected back into space by the solar wind or by the collisions that shaped the early solar system. Some of it may have been forged in the cores of earlier stars, transmuted from hydrogen into heavier elements by nuclear fusion, then scattered into space when those stars died. Some of it may have passed through other stellar systems, been incorporated into their planets or their comets, and then released again when those systems evolved, or when gravitational interactions ejected the material back into the interstellar medium. The atoms drifting past Voyager carry no record of their journeys, no way to trace where they have been or what structures they once formed, but they are old, older than the Sun, older than Earth, and they have been part of the galaxy's slow churn for eons. Dust is present too, though Voyager's instruments are not designed to detect individual dust grains directly. Dust in the interstellar medium consists of tiny solid particles, most of them smaller than a micron, smaller than a bacterium, smaller than the wavelength of visible light, composed of silicates and carbonaceous materials and ices, depending on the temperature and the chemical composition of the gas from which they condensed. These grains absorb and scatter starlight, making distant stars appear dimmer and redder than they would if the space between them were truly empty, and they play a critical role in the chemistry of the interstellar medium, providing surfaces where atoms can meet and bond into molecules that would never form in the gas phase. The density of dust in the local interstellar cloud is low, perhaps 1 grain per few hundred cubic miles, but over the distances Voyager travels, even such a low density means that the spacecraft encounters a steady, almost imperceptible bombardment of tiny impacts, each one too small to cause damage, but collectively contributing to the slow erosion of the spacecraft's surfaces. The environment Voyager measures in interstellar space is not static. The instruments detect fluctuations in the electron density, in the strength and direction of the magnetic field, in the intensity of cosmic rays, all varying on timescales of days to weeks. Some of these fluctuations are intrinsic to the interstellar medium, caused by waves and turbulence in the plasma, by the passage of shock waves from distant stellar events, by variations in the distribution of matter and energy within the local interstellar cloud. Others may be related to the Sun's activity, because even though Voyager has crossed the heliopause, the boundary itself is not static. It moves in response to changes in the solar wind's pressure, advancing outward when the wind is strong and retreating inward when the wind weakens, and Voyager may at times find itself on one side of the boundary or the other, depending on where the boundary has shifted. The spacecraft is also moving deeper into interstellar space with each passing day, traveling at about 38,000 miles per hour relative to the Sun, and the properties of the interstellar medium may change gradually with distance as the spacecraft samples different parts of the local interstellar cloud or eventually crosses into a different cloud altogether. The fact that interstellar space is not uniform, not a single homogeneous medium, but a complex, structured environment with variations on every scale, from millions of miles to light years, means that the data Voyager returns will continue to reveal new features and raise new questions for as long as the spacecraft's instruments keep functioning. The crossing of the heliopause was not an ending, but a beginning, the start of a new phase of the mission, where every measurement samples a region of space that no human-made instrument has ever explored before. The particle density Voyager measures in interstellar space, roughly 1 atom per cubic inch, is an average, a statistical quantity that represents the mean number of atoms the spacecraft's instruments would detect if they could sample a large volume over a long period. But the atoms themselves are not distributed uniformly. They clump and thin, responding to forces and processes that operate on scales both smaller and larger than the spacecraft can directly observe. In some regions, the density might be twice the average. In others, half. The variations are subtle, difficult to distinguish from the noise inherent in any measurement of such sparse quantities, but they are real, and they tell a story about the structure of the interstellar medium and the events that have shaped it. To measure particle density at such low levels requires patience and precision. Voyager's plasma wave instrument, which detects the oscillations of electrons in the plasma, provides the most direct measurements of the electron density in interstellar space. The instrument works by listening to the natural electromagnetic waves that propagate through the plasma. Waves generated by the thermal motion of the electrons themselves or by disturbances passing through the medium. These waves occur at specific frequencies determined by the electron density. The denser the plasma, the higher the frequency, and by measuring the frequency of the waves, the instrument can infer the density of electrons producing them. The frequencies are in the range of a few kilohertz, far below the range of human hearing, but analogous to sound waves in the sense that they represent oscillations of the medium, compressions and rarefactions of the electron population that propagate outward from their source. The waves are not always present. They require some kind of disturbance to generate them, some event or process that pushes electrons out of equilibrium and sets them oscillating. In the Helios heath, the turbulent solar wind provided a continuous source of disturbances, and the plasma wave instrument detected signals almost constantly, recording the chaotic hum of the solar wind's interactions with itself and with the interstellar medium pressing inward. In interstellar space, the medium is calmer, and the instrument detects plasma waves only occasionally, when something, perhaps a shock wave from a distant stellar event, perhaps a transient interaction with the edge of the heliosphere, stirs the electrons into motion. During these events, the instrument can measure the wave frequencies and determine the electron density with reasonable accuracy. Between events, during the long stretches when no waves are detected, the density must be inferred from other data or assumed to remain close to its last measured value. The measurements that Voyager has returned show that the electron density in the local interstellar medium is higher than it was in the outer Helios heath, but still extraordinarily low, around 10,000 electrons per cubic inch, give or take a few thousand, depending on the location and the time. This is consistent with what astronomers expected, based on observations of starlight passing through the region, which show absorption features characteristic of a partially ionized plasma with a density in this range. But the spacecraft's direct measurements have revealed variations and fine structure that could not be detected from a distance. Fluctuations in the density on scales of tens or hundreds of millions of miles, changes that occur over weeks or months as Voyager drifts through different parts of the local interstellar cloud. Some of these variations may be related to the interface between the local interstellar cloud and the surrounding local bubble. The cloud is not an isolated entity, but a structure embedded in a larger, hotter medium, and the boundary between them is not a sharp surface, but a transition zone where the cooler, denser cloud material mixes with the hotter, thinner bubble material. Voyager, depending on its exact trajectory through this region, may be sampling parts of the cloud that are closer to the core, where the density is higher, or parts that are nearer to the edge, where the cloud is beginning to dissipate into the surrounding bubble. The spacecraft's motion at 38,000 miles per hour means that it covers about 330 million miles per year, or roughly half a light month, and over the course of a few years, It can traverse distances comparable to the scale of the variations within the cloud. Other variations may reflect the presence of structures within the cloud itself, filaments or sheets of denser material, regions where the gas has been compressed by magnetic forces or by the passage of old shock waves, or voids where the density is lower than average. The interstellar medium, even in a relatively quiescent region like the local interstellar cloud, is not smooth or featureless. It has texture, shaped by the interplay of gravity, pressure, and magnetic forces, by the slow drift of matter responding to the galaxy's rotation, by the remnants of past events whose effects have not yet fully dissipated. These structures are invisible to the eye, and even to most telescopes, because the densities involved are so low that the material does not emit or absorb enough light to be detected at any appreciable distance. Only by traveling through the region with instruments sensitive enough to count individual particles can the structure be mapped and understood. The neutral hydrogen atoms, which make up the majority of the mass in the interstellar medium, are even harder to measure directly than the electrons and ions. Voyager's plasma science instrument, which measures charged particles, cannot detect neutral atoms at all. The spacecraft does carry an instrument designed to detect neutral atoms from outside the solar system, the low-energy charged particle instrument, which can measure ions created when neutral interstellar atoms enter the heliosphere and become ionized by the solar wind. But this instrument measures the interstellar atoms indirectly from inside the heliosphere before Voyager crossed the heliopause. Once the spacecraft entered interstellar space, surrounded by neutral atoms but no longer in a region where those atoms are being ionized in significant numbers, the instrument's ability to measure them directly disappeared. The abundance of neutral hydrogen in the local interstellar medium must therefore be inferred from other observations, from the absorption of starlight by hydrogen atoms along different lines of sight, from theoretical models of how the atoms are distributed, and from the ratio of neutral atoms to ions measured by other spacecraft in different regions of the heliosphere. The inferred density of neutral hydrogen near Voyager is roughly 10 times higher than the electron density, meaning that most of the matter in the local interstellar medium is neutral rather than ionized. This is typical for a relatively cool, low-density region like the local interstellar cloud, where the radiation field is not intense enough to keep most of the hydrogen ionized. The neutral atoms drift through space, unaffected by the magnetic fields and electric currents that govern the behavior of the plasma, moving under the influence of gravity and their own thermal velocities. They collide with ions and electrons occasionally, exchanging charge or energy, but most of the time they travel alone, separated from their nearest neighbors by distances that, if scaled to human size, would be like scattering a handful of marbles across the surface of an entire continent and expecting them to interact. The sparseness of the medium means that collisions between particles are rare. A typical hydrogen atom in the local interstellar medium might travel for years, perhaps decades, before colliding with another atom. The mean free path, the average distance a particle travels between collisions, is measured in billions of miles, comparable to the size of the solar system itself. This is a profoundly different environment from anything experienced on Earth, where the air is dense enough that molecules collide billions of times per second, where even the thinnest laboratory vacuum contains enough particles that collisions occur frequently enough to maintain a kind of equilibrium. In interstellar space, collisions are so infrequent that the concept of temperature, which depends on the idea of particles sharing energy through collisions, begins to lose its usual meaning. Cosmic rays arrive at Voyager from every direction, a constant rain of particles moving at velocities so close to the speed of light that time itself, from their perspective, passes differently than it does for anything at rest. They are not rays in the sense of light rays. The name is a historical artifact from the early 20th century, when scientists first detected them and did not yet understand what they were. But individual atomic nuclei, stripped of their electrons, accelerated to energies that dwarf anything produced by natural processes on Earth. The lowest energy cosmic rays that Voyager detects carry energies of a few 100 million electron volts, roughly 100 times the energy released when a single atom of uranium undergoes fission. The highest energy cosmic rays ever detected, though not by Voyager, carry energies equivalent to a baseball thrown at 60 miles per hour, except that energy is concentrated in a single subatomic particle, a proton or a heavier nucleus, traveling so fast that its mass, from the perspective of a stationary observer, is thousands of times greater than its rest mass. The sources of cosmic rays are scattered throughout the galaxy and beyond. Most originate in supernova remnants, the expanding shells of gas and debris left behind when massive stars explode. These shells, moving outward at thousands of miles per second, create shock waves where they collide with the surrounding interstellar medium, and at these shock fronts, charged particles can be caught and accelerated, bouncing back and forth between the shock wave and the magnetic fields ahead of it, gaining energy with each crossing until they reach velocities that allow them to escape into interstellar space. The process is called diffusive shock acceleration, and it can operate for thousands of years after a supernova, gradually accelerating particles to higher and higher energies as long as the shock wave remains strong and the magnetic fields remain tangled enough to trap the particles. Other sources contribute as well. Pulsars, the rapidly rotating neutron stars left behind by some supernovae, generate intense magnetic fields that can accelerate particles in their vicinity. Stellar winds from massive, luminous stars create their own shock waves when they collide with the interstellar medium. And at the very highest energies, cosmic rays may come from sources outside the galaxy entirely, from active galactic nuclei, where supermassive black holes devour matter and eject jets of plasma at relativistic speeds. The particles, once accelerated, travel through the galaxy for millions of years, their paths bent and twisted by the galaxy's magnetic field, so thoroughly scrambled that by the time they reach the solar system, it is impossible to trace them back to their sources. A cosmic ray arriving at Voyager today might have been accelerated in a supernova explosion that occurred 10,000 years ago, or 100,000 years ago, or longer, and it might have traveled 100 light-years to reach the spacecraft, or 1,000 or 10,000, spiraling through the galaxy's magnetic field, moving generally outward from the galactic center toward the halo and back again, drifting with the field's slow evolution. The cosmic rays that Voyager detects are, in a sense, messengers from the galaxy's violent past, carrying information about events that occurred long before humans existed, before Earth had continents or an oxygen-rich atmosphere, before the Sun entered the local interstellar cloud. Inside the heliosphere, the solar wind provides partial shielding against these particles. The wind's magnetic field, though weak and tangled, is strong enough to deflect lower-energy cosmic rays, preventing them from reaching the inner solar system or reducing their numbers to a fraction of what exists in interstellar space. Higher-energy cosmic rays, those with enough momentum to push through the magnetic barriers, penetrate more easily, but even they are affected, their intensity reduced by interactions with the wind's turbulent fields. The shielding is not constant. It varies with the 11-year solar cycle, becoming weaker when the Sun is less active and the solar wind is calmer, stronger when the Sun is more active and the wind is more intense and more turbulent. At Earth, the cosmic ray flux varies by perhaps 10 to 20% over the course of a solar cycle, enough to be measured but not enough to pose a significant hazard to life on the surface, where the atmosphere provides the primary protection. When Voyager crossed the heliopause, the cosmic ray intensity increased sharply, just as the scientists had predicted. The increase was not the same for all energies. Lower-energy cosmic rays, those most easily deflected by the solar wind, showed the largest jump, roughly doubling in intensity over the course of a few weeks. Higher-energy cosmic rays, which had already been penetrating into the heliosphere in significant numbers, increased more modestly, by perhaps 10 to 20%. The pattern of the increase confirmed that the spacecraft had crossed a real boundary, a place where the solar wind's shielding effect ended and the full intensity of the galactic cosmic ray background became measurable. The data also revealed something unexpected. The cosmic ray intensity did not simply jump to a constant level and remain there. It continued to fluctuate, varying by 10% or more over timescales of weeks to months, suggesting that the interstellar medium itself is not uniform, that there are variations in the cosmic ray density or in the magnetic fields that guide them, structures that Voyager is now sampling, as it drifts deeper into interstellar space. The composition of the cosmic rays provides additional information about their sources and their history. Most are hydrogen nuclei, protons, accounting for about 90% of the total. Roughly 9% are helium nuclei, alpha particles identical to those emitted by radioactive decay, but moving far faster. The remaining 1% consists of heavier nuclei, carbon, oxygen, nitrogen, iron, and trace amounts of nearly every element in the periodic table up to uranium. The relative abundances of these elements differ from the abundances found in the Sun or in the Earth, reflecting the fact that cosmic rays are not a representative sample of ordinary matter, but a biased sample, enriched in elements that are more easily accelerated or that survive the journey through the galaxy, without being destroyed by collisions. Some of the heavier nuclei show evidence of having been broken apart by collisions with interstellar gas during their journey, fragmenting into lighter elements and creating isotopes that are rare in nature but common in cosmic rays. Voyager's detectors measure not just the flux of cosmic rays, but also their energy spectrum, the distribution of particles across different energies. The spectrum follows a power law, a mathematical relationship where the number of particles decreases steadily as the energy increases, with roughly 10 times fewer particles at 10 times the energy and 100 times fewer at 100 times the energy. This pattern extends across an enormous range, from energies of a few hundred million electron volts up to energies a billion times higher, measured by detectors on Earth and on satellites. The power law reflects the universal nature of the acceleration mechanisms that produce cosmic rays, the way shock waves and magnetic fields can amplify small differences in particle energy into large differences over time, preferentially accelerating some particles to very high energies while leaving most at lower energies. The fact that cosmic rays exist at all, that the galaxy is filled with high-energy particles traveling at relativistic speeds, has consequences for the evolution of planetary atmospheres, for the chemistry of the interstellar medium, for the ionization state of the gas in regions far from any star. Cosmic rays ionize atoms, stripping electrons and creating the low-level plasma that permeates even neutral clouds. They trigger chemical reactions, breaking apart molecules and allowing new ones to form. They deposit energy into the gas, heating it slightly, maintaining a temperature floor even in regions where starlight is too faint to provide significant heating. In the heliosphere, their influence is secondary to the Sun's, but in interstellar space they are one of the primary sources of ionization and energy, a background radiation field that affects every atom and molecule, however rarely those interactions occur. The magnetic field that Voyager measures in interstellar space does not point back toward the Sun. This might seem unremarkable. Why would the interstellar field have any particular orientation relative to a single star among billions? But it carries significance because it reveals how the Sun's magnetic field, carried outward by the solar wind, connects or fails to connect with the larger galactic field that threads through the space between stars. The question of connection is not merely geometric but physical, because magnetic field lines in a plasma can merge and reconnect, joining fields that were previously separate and allowing energy and particles to flow along pathways that did not exist before. At the heliopause, where the Sun's field meets the interstellar field, the potential for reconnection depends on the relative orientation of the two fields, on the angles at which they approach each other, and on the turbulence and density of the plasma on both sides of the boundary. Voyager's magnetometer, recording the field's direction continuously as the spacecraft moved through the heliosheath and across the heliopause, detected a gradual change rather than a sudden reorientation. Inside the heliosheath, the Sun's magnetic field pointed outward from the star, twisted into a spiral pattern by the Sun's rotation, but compressed and tangled by the resistance from the interstellar medium. The field's direction varied chaotically, swinging through large angles over the course of hours or days, never settling into a stable configuration. As Voyager approached the heliopause, the fluctuations diminished, and the field began to align more consistently in a direction that was neither radial from the Sun nor aligned with the expected orientation of the interstellar field. The transition took months, a slow drift rather than an abrupt shift, and even after the spacecraft crossed the heliopause, after the solar wind particles disappeared and the cosmic rays increased. The magnetic field continued to evolve, gradually rotating toward the orientation that astronomers had predicted for the interstellar field in this region of the galaxy. The expected orientation, based on observations of distant stars and on models of the galaxy's large-scale magnetic structure, was roughly parallel to the plane of the Milky Way's disk, pointing in a direction that reflects the galaxy's rotation and the motion of charged particles on scales spanning thousands of light-years. The field in the local interstellar cloud, according to these predictions, should point toward a region of the sky located in the constellation Scorpius, offset by about 30 degrees from the direction of the galactic center. Voyager's measurements, after the spacecraft had been in interstellar space for several years, confirmed this orientation to within a few degrees, a remarkable agreement given the uncertainties in the models and the complexities of the region. But the fact that the transition took so long that the field did not immediately snap to the interstellar orientation upon crossing the heliopause suggested that the boundary region is more complicated than a simple interface between two distinct magnetic domains. One possibility is that the magnetic field in the immediate vicinity of the heliopause is a hybrid, a mixture of field lines that originated in the Sun and field lines that came from the interstellar medium, all tangled together by the turbulence and compression that occur where the solar wind meets the galactic plasma. In this picture, some field lines reconnect, merging the Sun's field with the interstellar field and creating pathways that span the boundary, while other field lines remain separate, piling up against each other without merging. The relative balance between reconnection and pile-up depends on the local conditions, on the density of the plasma, on the strength and orientation of the fields, on the presence of turbulence that can bring field lines into close proximity and allow them to merge. Voyager, crossing the heliopause at one specific location, sampled one particular configuration of this hybrid region, but the configuration likely varies with position, differing at the leading edge of the heliosphere, where the Sun's motion through the interstellar medium creates a bow shock, from the sides or the trailing edge, where the heliosphere stretches into a tail. Another unexpected feature of the magnetic field data was its strength. Inside the heliosheath, the field was compressed by the resistance from the interstellar medium, reaching strengths of several tenths of a nanogauss, still extraordinarily weak by terrestrial standards, but stronger than the field had been farther inward in the solar system. Scientists expected that upon crossing the heliopause, the field strength would drop, because the interstellar field, uncompressed by the solar wind, should be weaker than the compressed solar field in the heliosheath. But Voyager's measurements showed that the field strength remained roughly constant, or even increased slightly, after the crossing. This suggested that the interstellar field in the local interstellar cloud is stronger than the models had predicted, or that the boundary region itself enhances the field through processes that are not yet fully understood, perhaps through the compression of interstellar plasma as it encounters the heliosphere, or through the generation of currents and waves that amplify the field locally. The persistence of a relatively strong magnetic field in interstellar space has implications for how cosmic rays propagate through the region. Magnetic fields deflect charged particles, bending their paths and scattering them, and a stronger field means more deflection, more scattering, longer travel times for particles trying to cross a given distance. The cosmic rays that Voyager detects in interstellar space have been traveling through the galaxy's magnetic field for thousands or millions of years, their paths so thoroughly scrambled that their arrival directions carry no information about their sources. But the local field, the field in the immediate vicinity of the spacecraft, determines how quickly cosmic rays can diffuse into the heliosphere, how effective the solar wind's shielding is, and how the cosmic ray intensity varies with distance from the heliopause. A stronger interstellar field means that cosmic rays approaching the heliosphere are more likely to be deflected away or slowed, reducing the flux that reaches the inner solar system and making the heliosphere's shielding effect more pronounced. The magnetic field also affects the shape of the heliosphere itself, because the interstellar field exerts a pressure that pushes against the heliopause from the outside, just as the solar wind pushes outward from the inside. If the interstellar field is stronger in one direction than another, The heliosphere will be compressed more in that direction and extended farther in the opposite direction, creating an asymmetry that depends on the orientation of the field relative to the Sun's motion through the galaxy. Models of the heliosphere, incorporating the measured strength and orientation of the interstellar field, suggest that the boundary may be elongated, with the heliopause lying closer to the Sun in the direction perpendicular to the interstellar field and farther from the Sun in the directions parallel to the field. Voyager, crossing at one point along the boundary, measured a distance from the Sun to the heliopause of about 11 billion miles, but other parts of the boundary may lie closer or farther, and the overall shape of the heliosphere remains uncertain. The data Voyager has returned, the magnetic field measurements, the particle densities, the cosmic ray intensities, provide snapshots of the conditions at specific locations along the spacecraft's trajectory, but they do not provide a complete picture of the heliosphere's structure or of the interstellar medium's properties across the region. The spacecraft is a single point moving through a vast three-dimensional space, and the properties it measures at one location may not apply just a few million miles away, where the density or the magnetic field or the balance of forces might be different. To map the region fully would require multiple spacecraft, crossing the heliopause at different locations and at different times, sampling the variations and building a comprehensive picture of how the boundary behaves and how the interstellar medium is structured in the Sun's immediate vicinity. The texture of interstellar space, as revealed by Voyager's instruments, is not smooth but granular, structured across a wide range of scales, from millions of miles to light years. At the smallest scales, the instruments can resolve distances comparable to a few million miles traversed by the spacecraft over the course of weeks. The electron density fluctuates, rising and falling by factors of 2 or 3, sometimes more. These variations are not random noise in the data, but real structures in the plasma, regions where the matter has been concentrated or diluted by processes that operate on timescales of days to months. Some of the structures may be waves, oscillations of the plasma density and magnetic field, that propagate through the medium at speeds determined by the field's strength and the plasma's temperature. Others may be more static features, clouds within clouds, pockets of denser or thinner gas embedded in the larger structure of the local interstellar cloud. The waves, if that is what they are, would be moving so slowly relative to the spacecraft's velocity that Voyager, from its own perspective, would encounter them as stationary features, structures that the spacecraft passes through rather than waves that pass over it. A typical wave in the interstellar plasma, driven by magnetic or thermal pressure, might propagate at a few tens of miles per second, fast by terrestrial standards, but far slower than Voyager's velocity of 38,000 miles per hour. The spacecraft, moving through such a wave field, would sample the density variations in sequence, recording them as fluctuations in time that reflect the spatial structure of the medium. Distinguishing between a wave and a static structure requires additional information, measurements of the magnetic field orientation, of the particle velocities, of the temperature, because waves carry with them specific patterns of correlation between these quantities, patterns that static structures do not necessarily exhibit. The magnetic field fluctuations that Voyager measures show correlations with the density fluctuations, suggesting that at least some of the structures are magnetized, that the field and the plasma are coupled together and respond jointly to whatever processes created them. In a magnetized plasma, the field and the matter cannot move independently. The field lines are, in a sense, frozen into the plasma, carried along by its motion, and any compression or rarefaction of the plasma also compresses or stretches the field. This coupling means that disturbances in the plasma, whether they are waves or static structures, necessarily involve both the matter and the field, and the two must vary together in ways that preserve certain physical relationships. The field strength should increase where the density is higher and decrease where the density is lower, unless other forces are at work to break the coupling. Voyager's data, showing that the field and the density do vary together, confirm that the medium is behaving as a magnetized plasma should, responding to forces in ways that are consistent with the known physics of such systems. But the data also contain surprises, features that were not anticipated and that do not fit neatly into the existing models of the interstellar medium. One such surprise is the presence of periodic or quasi-periodic variations in the density and magnetic field, oscillations that repeat on timescales of a few weeks or a few months, suggesting the presence of large-scale waves or structures with preferred wavelengths. The origin of these oscillations is not clear. They could be waves generated by the interaction of the heliosphere with the interstellar medium, disturbances that propagate outward from the heliopause and into the surrounding space, or they could be waves that originated far from the Sun, created by distant events and now washing through the region where Voyager happens to be. Distinguishing between these possibilities requires more data, observations that extend over longer periods and that sample the medium at different distances from the heliopause. But the spacecraft's power supply is limited, and the instruments will not continue functioning indefinitely. Another surprise is the variability of the cosmic ray intensity, which does not remain constant even after accounting for the 11-year solar cycle and the expected modulation by the heliosphere's changing size. The cosmic rays Voyager detects increase and decrease by 10% or more over timescales of months, variations that are too large and too rapid to be explained by the spacecraft's motion through a uniform background. The variations suggest that the cosmic ray density in the local interstellar medium is not uniform, that there are regions where the intensity is higher and regions where it is lower, and that these regions are large enough that Voyager takes months to cross them. The structures could be related to variations in the magnetic field, which guides and scatters cosmic rays, or to variations in the density of the plasma, which affects how cosmic rays propagate through the medium. Or they could be related to the sources of the cosmic rays themselves, to the distribution of supernova remnants and other accelerators within the galaxy, whose effects may create gradients or enhancements in the cosmic ray density that persist across distances of tens or hundreds of light years. The temperature of the interstellar medium, as inferred from the velocities of the particles Voyager detects, is also not uniform. The electrons measured by the plasma wave instrument have temperatures of several thousand degrees Kelvin, but the ions, if they could be measured directly, which Voyager's instruments cannot do once the spacecraft is in interstellar space, are expected to have different temperatures, possibly higher or possibly lower depending on the balance of heating and cooling processes affecting them. In a collisionless plasma, where collisions between particles are so rare that they cannot maintain thermal equilibrium, different particle species can have different temperatures, each evolving independently according to the forces acting on it. The electrons, being lighter and more mobile, respond more quickly to electric fields and to the oscillations of the magnetic field, and they can be heated by processes that leave the ions largely unaffected. The ions, being heavier, are more sluggish but carry more kinetic energy per particle at a given temperature, and they can be heated by different processes, by the compression of the plasma, by the passage of shock waves, by interactions with magnetic turbulence. The difficulty in measuring the properties of the interstellar medium directly, with instruments that were designed decades ago for a different purpose, means that much of what scientists know about the region comes not from the measurements themselves, but from the interpretation of those measurements, from the models and theories used to translate the raw data into physical quantities. The electron density, for instance, is not measured directly by counting electrons, but inferred from the frequency of plasma waves, which in turn depends on assumptions about the wave propagation and the plasma's composition. The temperature is inferred from the wave amplitudes and from comparisons with other measurements, not from direct observations of particle velocities. The magnetic field is measured directly by the magnetometer, but interpreting what that field means, whether it is the undisturbed interstellar field or a perturbed version of that field, whether it represents the average properties of the medium or a local anomaly, requires context and comparison with models. The models themselves are built from a combination of theory, observation, and educated guesswork, attempting to describe a medium that is vastly more complex than the simple approximations that make the mathematics tractable. The local interstellar cloud is not a static, uniform blob of gas, but a dynamic, evolving structure shaped by processes operating on timescales ranging from days to millions of years. It is embedded in the local bubble, itself a transient feature created by supernovae, that will eventually dissipate as the hot gas cools and mixes with the surrounding medium. The cloud moves through the bubble, and the sun moves through the cloud, and the galaxy rotates beneath it all, carrying stars and gas and magnetic fields in patterns that shift and evolve over eons. Voyager's measurements provide a snapshot of this system at one moment, a single line through a multidimensional, time-varying structure. And from that single line, scientists must attempt to reconstruct the whole. The surprises in Voyager's data are not dramatic revelations that overturn fundamental physics, but subtle discrepancies between what was expected and what was measured, small differences that suggest the models were incomplete or that the local interstellar medium is more complex than the observations from Earth could reveal. These are the kinds of surprises that science values most, not the sudden appearance of something entirely unprecedented, but the quiet discovery that the details matter, that the assumptions embedded in the models were not quite right, that nature has arranged things in ways that are consistent with known laws but configured differently than anticipated. One such surprise concerns the temperature structure at the heliopause. Models predicted that the solar wind, as it slows and compresses in the heliosheath, would heat to temperatures of hundreds of thousands of degrees, the kinetic energy of the wind's outward motion converting into thermal energy as the particles collided and jostled against one another in the increasingly crowded space. Voyager's instruments, however, did not detect the expected heating. The temperatures in the heliosheath remained low, only a few tens of thousands of degrees, and the transition across the heliopause did not involve the dramatic jump in temperature that the models had predicted. The solar wind particles, as they approached the boundary, seemed to disappear rather than heat up, as if they were being absorbed or deflected or transformed in some way that removed them from the population the instruments could detect. The puzzle remains unresolved. The data indicate that something is happening to the solar wind near the heliopause, some process or combination of processes that carries away the particles' energy without raising the temperature in the way that simple compression would predict. Another discrepancy involves the cosmic ray gradient, the rate at which cosmic ray intensity changes with distance from the heliopause. Inside the heliosphere, cosmic rays decrease in intensity as they move inward toward the sun, deflected and scattered by the solar wind's magnetic field. The models predicted that outside the heliopause, in interstellar space, the cosmic ray intensity should remain relatively constant, varying only slowly with distance as the spacecraft moved through the local interstellar cloud. But Voyager's measurements show a more complicated pattern. The cosmic ray intensity increased rapidly immediately after the crossing, as expected, but then continued to increase more gradually as the spacecraft moved farther from the heliopause, rising by 10% or more over a distance of a few 100 million miles. This gradient suggests that the heliopause itself affects the cosmic ray distribution in the surrounding interstellar medium, perhaps by reflecting some cosmic rays back into interstellar space, or by creating a region of enhanced turbulence that scatters cosmic rays and reduces their ability to approach the boundary. The exact mechanism is unclear, and the gradient may not persist indefinitely. It may level off at some distance, or it may continue as far as Voyager can measure, or it may vary depending on changes in the heliosphere's size and shape. The magnetic field orientation near the heliopause also presented puzzles. Scientists had expected that if the Sun's magnetic field and the interstellar magnetic field reconnected at the boundary, the reconnection would create a specific pattern of field lines, a configuration where some lines connect the Sun to the interstellar medium and others remain separate, with the transition occurring in a narrow layer at the heliopause. Voyager's data, however, show that the field's orientation changed gradually over a region spanning millions of miles, with no clear evidence of the sharp transition that reconnection would produce. This could mean that reconnection is not occurring, at least not in the simple, efficient way the models predicted, or it could mean that reconnection is occurring, but in a patchy, intermittent manner, with some field lines merging while others do not, creating a complex three-dimensional structure that a single spacecraft cannot fully map. The absence of certain expected phenomena is as informative as the presence of surprises. Voyager did not detect a bow shock, the sharp boundary where the interstellar medium flowing past the heliosphere, should pile up and heat as it encounters the obstacle. Theoretical models for decades had predicted that such a shock should exist, located somewhere beyond the heliopause, perhaps a few billion miles farther out, marking the place where the supersonic flow of the interstellar medium relative to the heliosphere transitions to subsonic flow. But Voyager crossed the heliopause and continued outward, and the instruments saw no evidence of the shock, no sudden increase in temperature, no jump in density, no change in the magnetic field that would indicate a shock crossing. Either the shock is farther away than the models predicted, perhaps so far that Voyager will never reach it before the spacecraft's power runs out, or the shock does not exist at all because the relative velocity between the Sun and the interstellar medium is too low for a shock to form, or because the medium's properties are such that the transition is smooth rather than abrupt. The non-detection of the bow shock is not necessarily a failure of the models. Models are simplifications, built on assumptions that are chosen to make the mathematics manageable and the predictions testable. They represent idealized versions of reality, where the interstellar medium is uniform, where the heliosphere is symmetric, where the magnetic fields are aligned in convenient ways. Real environments are messier. The local interstellar cloud has structure. The heliosphere is asymmetric, the magnetic fields are tangled and variable, and all of these complications can shift the location of a boundary or blur a sharp transition into a gradual one, or eliminate a feature that would exist in the idealized case but not in the actual complex reality. The absence of the bow shock does not mean the models were wrong in any fundamental sense. It means they were incomplete, missing some details or some effects that turned out to be important in this specific case. The uncertainties in Voyager's measurements also contribute to the sense that the picture remains incomplete. Every measurement carries errors, uncertainties that arise from the limitations of the instruments, from the statistical nature of counting particles, from the need to infer properties indirectly when direct measurements are not possible. The electron density, for instance, is inferred from plasma wave frequencies, and those frequencies are measured with a precision of perhaps a few percent, which translates into uncertainties in the density of 10 or 20%. The magnetic field is measured directly, but the calibration of the magnetometer after decades in space may have drifted slightly, introducing small systematic errors that accumulate over time. The cosmic ray counts, being statistical, fluctuate naturally, and distinguishing real variations in the cosmic ray intensity from the random fluctuations requires long averaging times and careful analysis. These uncertainties do not invalidate the data. Voyager's measurements remain the best, and in many cases the only direct measurements of the interstellar medium in the Sun's vicinity. But they do mean that the conclusions drawn from the data must be tentative, subject to revision as more data arrive or as the analysis techniques improve. There is also the question of how representative Voyager's measurements are of the interstellar medium as a whole. The spacecraft has sampled one specific trajectory, one line through a vast heterogeneous medium, and the properties it measures along that line may not be typical of the region more broadly. The electron density, the magnetic field strength, the cosmic ray intensity. All of these may vary from place to place within the local interstellar cloud, and Voyager's path may have taken it through regions that are denser or thinner, more magnetized or less magnetized, more turbulent or calmer than average. Without other spacecraft making measurements at other locations, there is no way to know whether the values Voyager reports are representative of the cloud as a whole or specific to the particular region the spacecraft happens to be traversing. These limitations are not unique to Voyager or to the study of the interstellar medium. They are inherent in the scientific process, in the attempt to understand complex systems from incomplete information, to infer general principles from limited observations, to construct models that capture the essential features of reality, while necessarily omitting details that cannot be observed or calculated. The progress that Voyager enables is incremental, a step forward in understanding rather than a final answer, and the questions it raises are as valuable as the measurements it provides. The silence in the data is as important as the signals. There are phenomena that the models predict, but that Voyager has not observed, measurements that the instruments cannot make, questions that cannot be answered with the available data. Some of these absences reflect the limitations of the spacecraft, instruments that were turned off to save power, capabilities that were not included in the design because they were not anticipated to be necessary, sensitivities that are insufficient to detect phenomena that exist at levels below the detection threshold. Others reflect fundamental limits on what can be measured by a single spacecraft following a single trajectory through a medium that varies in space and time. Still others point to gaps in understanding, to processes or structures that the models did not predict and that the data, in their absence, cannot directly reveal. One of the most significant limitations is Voyager's inability to measure the composition of the interstellar medium in detail. The instruments can count particles and measure their energies, but they cannot determine what elements those particles are made of, beyond the broad distinction between electrons and ions, or in the case of cosmic rays, between protons and heavier nuclei. The neutral hydrogen atoms that make up most of the mass in the local interstellar medium are essentially invisible to Voyager's sensors. The spacecraft can infer their presence from other measurements, from the balance between neutral and ionized particles inferred from ultraviolet observations of distant stars, from theoretical models of how hydrogen behaves in the conditions thought to exist in the local interstellar cloud, but it cannot count them directly, or measure their velocity distribution, or determine whether they are distributed uniformly or concentrated in specific regions. This means that one of the most fundamental properties of the medium, the abundance and distribution of the dominant constituent, remains uncertain, known only indirectly, and subject to the assumptions that go into the models. Another limitation is the spacecraft's inability to see ahead. Voyager measures the environment where it is, at the moment the measurement is made, but it has no way to detect what lies ahead along its trajectory or to anticipate changes that will occur as it moves deeper into interstellar space. If the spacecraft is approaching a region where the density increases, or where the magnetic field changes direction, or where a shock wave from a distant stellar event is passing through, the first indication will be when the instruments begin to register the change, by which time the spacecraft is already in the midst of it. This reactive mode of observation means that the data are always trailing the reality, always responding to conditions rather than predicting them, and it limits the ability to study transient phenomena or to understand the spatial structure of features that the spacecraft encounters. The spacecraft's trajectory is also a limitation. Voyager 1 and Voyager 2 are moving in different directions, sampling different parts of the heliopause and different regions of the interstellar medium, but they are still just 2 points in a vast space. The heliosphere is billions of miles across, and the local interstellar cloud is light years in extent. And 2 trajectories, however carefully chosen, cannot capture the full complexity of either structure. The properties Voyager measures along its path may differ significantly from the properties just a few 100 million miles to the side, in directions the spacecraft is not traveling. The boundary between the heliosphere and interstellar space, for instance, may be closer to the Sun in some directions and farther in others, depending on the orientation of the interstellar magnetic field and the asymmetry of the solar wind, and Voyager's measurements at 2 specific crossing points cannot reveal the full 3-dimensional shape of the boundary. There is also the question of time. The conditions Voyager measures are not static. They change as the Sun's activity waxes and wanes, as the interstellar medium flows and fluctuates, as the heliosphere itself expands and contracts in response to variations in the solar wind. The heliopause is not a fixed boundary, but a dynamic interface that moves inward and outward by hundreds of millions of miles over the course of the solar cycle. And Voyager, moving outward at a constant velocity, may cross and recross the boundary multiple times, or may remain on one side while the boundary shifts back and forth around it. The data the spacecraft returns reflect conditions at specific moments, snapshots taken at intervals of seconds or minutes or hours, but the processes shaping those conditions operate on timescales ranging from days to years to millions of years, and disentangling the contributions of different processes requires observations that span multiple timescales, something that a single spacecraft, with a limited operational lifetime, can provide only partially. The power supply that keeps Voyager's instruments running is finite, and it is declining. The radioisotope thermoelectric generators that provide electricity to the spacecraft produce less power each year as the plutonium decays, and eventually the power will drop below the level needed to operate the instruments and the transmitter. The mission team has been managing the power carefully, turning off heaters and non-essential systems, choosing which instruments to keep running and which to shut down, but the decline is inexorable. The plasma science instrument on Voyager 1 failed years ago. A casualty of age and the harsh environment of space, and other instruments will follow as the power continues to drop. By the late 2020s, perhaps the early 2030s, the remaining instruments will have to be turned off one by one, and eventually the spacecraft will fall silent, no longer able to transmit data back to Earth. The data that have been collected up to that point will be all that Voyager can provide, a finite record of the conditions along a finite stretch of its trajectory, and everything beyond that will remain unobserved unless future missions venture into interstellar space. Even the data that Voyager does collect are subject to interpretation, and different scientists examining the same data can reach different conclusions about what they mean. The transition across the heliopause, for instance, was debated for years, with some researchers arguing that Voyager had crossed the boundary as early as 2010 or 2011, based on preliminary signatures in the data, while others maintained that the true crossing did not occur until 2012 or even later. The debate centered on which measurements were most definitive, whether the disappearance of solar wind particles was sufficient evidence, or whether the reorientation of the magnetic field was also necessary, or whether cosmic ray intensity alone could confirm the crossing. These disagreements were not trivial or pedantic. They reflected genuine uncertainty about what defines the heliopause and about how to interpret data that show gradual transitions rather than sharp boundaries. The eventual consensus that Voyager 1 crossed in August 2012 and Voyager 2 in November 2018 emerged only after years of analysis and after multiple lines of evidence began to converge, and even now some details remain debated. The interpretive challenges extend beyond the heliopause crossing to nearly every aspect of the data. The variations in electron density that Voyager detects could be waves, or they could be static structures, or they could be artifacts of the measurement process, fluctuations introduced by the instrument itself or by the way the data are processed. The magnetic field fluctuations could reflect real changes in the interstellar field, or they could be remnants of the solar wind's influence, or they could be generated by currents and instabilities in the plasma at the heliopause. The cosmic ray variations could indicate real spatial structure in the interstellar medium, or they could be temporal variations, changes in the galactic cosmic ray background that occur over months or years for reasons unrelated to Voyager's location. Distinguishing between these possibilities requires careful analysis, comparison with models, and often a willingness to accept that the available data are not sufficient to provide a definitive answer. The unknowns that remain are not failures of the mission, but reflections of the difficulty of the task. Voyager was designed to explore the outer planets, to study their atmospheres and magnetospheres and moons, and the fact that the spacecraft have gone on to explore the edge of the heliosphere and the beginning of interstellar space is a testament to the robustness of their design and the foresight of the mission planners, who anticipated that the spacecraft might last long enough to reach those distant regions. But the instruments were not optimized for studying the interstellar medium. They were not designed to measure neutral atoms, or to resolve small-scale structures, or to determine the composition of the plasma with high precision. They were designed to work in the environment of the solar system, where the densities are higher, the magnetic fields stronger, the phenomena more energetic. That they function at all in the tenuous, cold, quiet environment of interstellar space is remarkable, and the data they return, despite their limitations, provide insights that would be impossible to obtain any other way. Voyager continues outward. The spacecraft has no sense of crossing or arrival, no awareness that it has left one region and entered another. It measures what it encounters, transmits the data back across the widening gulf, and drifts onward at the same velocity it has maintained for decades. The sun behind it grows fainter, not in any dramatic way, but in the slow arithmetic of distance, a light that dims as the inverse square of separation, a gravity that weakens but never vanishes, an influence that tapers towards zero without ever quite reaching it. The boundary it crossed was real, marked by the disappearance of particles that had traveled billions of miles from the sun and by the arrival of particles that have never known the sun's touch. But the crossing did not feel like a threshold. There was no wall, no gate, no change visible to human eyes. Only the instruments could detect what had shifted, a ratio of densities, a reorientation of invisible field lines, an increase in the rain of particles from distant ancient stars. The frontier between the sun's domain and the galaxies is defined entirely by forces that operate below the threshold of perception, a border that exists only in the behavior of matter too sparse to see. The space beyond is not fundamentally different from the space within, not in texture or temperature or in any quality that would register as distinct to an observer standing on the spacecraft's surface. It is still a void, still cold, still silent. The atoms are slightly different, their origins more varied, their histories longer. The magnetic field points in a new direction, aligned with structures light years across, rather than with the rotation of a single star. The cosmic rays are more numerous, arriving from regions the heliosphere had kept at a distance. But these are changes of degree, adjustments in quantities that were already small. Interstellar space is not alien. It is simply farther from the influence that shaped the space closer in. What Voyager has found is not an answer, but a continuation of the question. The data reveal a medium that is more complex than the models anticipated, more structured, more variable, less uniform. They show a boundary that is real but not sharp, a transition that unfolds over distances comparable to the size of the inner solar system. They confirm that the sun, like all stars, creates a bubble of influence around itself. But they also show that the bubble is not isolated, that it exists within a larger context, embedded in a medium that has its own properties and its own history. The heliosphere and the interstellar medium are not separate realms but parts of a continuum, regions that differ in their details but share the same fundamental physics, the same laws governing how matter and energy and fields interact across the emptiness. The scientists who study the data will continue to debate the details, to refine the models, to propose new explanations for the features that were unexpected. The spacecraft will continue to drift outward until its power fails, measuring the medium for as long as the instruments can function, sampling conditions that no one will be able to observe again until another mission ventures into this region, if one ever does. The knowledge that Voyager provides will remain incomplete, a single thread through a vast tapestry, but it will be the only direct knowledge humanity has of what lies beyond the sun's immediate reach, the only ground truth against which theories and models can be tested. The silence will deepen. Eventually, the signal will fade, not because the transmitter stops, but because the distance becomes too great, the power too weak, the noise of the galaxy too loud. The data stream that has flowed back to Earth for decades will thin and then cease, and Voyager will become an artifact, a relic drifting through interstellar space with no connection to the world that built it. The spacecraft will continue its journey for millions of years, perhaps billions, moving through regions that will never be measured, encountering structures that will never be recorded, crossing boundaries that will go unnoticed because there will be no instruments left to notice them. But for now, the data still arrive, carrying information about a place 15 billion miles away, a place where the sun's wind has stopped and the galaxy's presence is felt for the first time. The measurements are small, incremental additions to a picture that will never be complete, but they are real, and they are enough to show that the boundary exists, that it can be crossed, that beyond the reach of the sun, there is something else, something older and larger, and equally full of structure and mystery. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.